Hey everyone, today we are diving into something wild, a question that literally pushes physics to its breaking point. We're going to explore the ultimate limit of matter and we'll be using a legendary 1939 paper as our guide. So let's take a trip to the very edge of what we know.
So what's the big question here? It's this. What's the absolute maximum weight a star can hold before it just collapses forever? Before its own gravity just crushes it out of existence and turns it into a black hole? And listen, this isn't just some abstract thought experiment. This is at the heart of understanding the most violent, incredible events in the entire universe.
All right, so the object at the center of this whole mystery is the neutron star. And honestly, these things are just bananas. I mean, try to wrap your head around this. You take our entire sun with all its mass and you crush it down into a ball the size of a city. The density is something like 100 trillion times that of water. A single teaspoon of this stuff would weigh billions of tons. It's just mind-bending. So, you've got this insane object. How do you even begin to figure out its breaking point? Well, the first step for physicists was to go back to basics. They started with what they knew best, Isaac Newton's classical physics. And one of the first people to really take a crack at this was the Soviet physicist Lev Landau, an absolute genius. This was back in the 1930s. He had this idea to treat the core of the star as something called a degenerate Fermi gas. Now that sounds complicated, I know, but stick with me. So what on earth is a degenerate Fermi gas? Okay, imagine you're at the most packed concert ever. You are literally shoulder to shoulder with everyone. You can't get any closer, right? There's no more room. That's kind of what's happening here. The particles, in this case neutrons, are so jammed together that a weird rule from quantum mechanics kicks in. It basically says, nope, you can't get any closer, and it creates this huge outward push, a pressure that fights back against gravity's insane crush. So Landau runs the numbers with this model, and the result he gets is just massive. He calculates that a neutron star could get up to 6 times the mass of our sun before collapsing. 6! And for a while, that was the number. Everyone thought, okay, that's the limit. But there was a catch, a big one. See, a neutron star isn't just heavy. It's so ridiculously dense that the good old rules of Newtonian physics, they just don't cut it anymore. They start to fall apart. It was time for a whole new set of rules, and those rules were written by Albert Einstein. Yeah, you see, Newton thought of gravity as just a force, an invisible rope pulling things together. But when you get to the crazy extremes of a neutron star, Einstein's theory tells us something way weirder is happening. The gravity is so powerful, it's literally bending and warping the fabric of space and time itself. This isn't some minor tweak to the math. It's a fundamental shift in how we see the universe. And this really lays it out perfectly. On one side, you've got Newton's idea. Space is just this boring, static backdrop, like a stage where things happen. But on the other side, you have Einstein's general relativity. And here, space-time is a dynamic fabric. Mass and energy actually tell this fabric how to bend, and in turn, that bending tells matter how to move. For a neutron star, that bend is, well, it's less of a bend and more of a deep, deep well. So what does this all mean? It means Landau's calculation had to be redone, from scratch. This time, using Einstein's incredibly complex equations. And let me tell you, the answer they got was not just a little different. It was a shock. And this is where our main characters enter the story. We're talking about J. Robert Oppenheimer. Yep, that Oppenheimer. And his student, George Volkoff. This was in 1939, and they decided, okay, let's take on this beast. They were going to apply Einstein's general relativity to this whole neutron star problem. And the work they did, which is all laid out in their paper, was just a monster of a calculation. I mean, first they had to model the star as a perfect fluid. Then they had to apply Einstein's field equations, which are notoriously difficult. Then they plugged in the physics for that neutron gas we talked about. And finally, they had to crunch all the numbers to find that one single point where gravity just becomes unstoppable. And the result? It was absolutely staggering. It didn't just tweak Landau's number, it blew it out of the water. What their math showed was that in this extreme, relativistic world, gravity is a much, much more vicious beast than anyone had imagined. So, what was the number? Get this, the new limit wasn't anywhere near 6 solar masses, it was less than 1. Oppenheimer and Volkoff's calculations showed that the absolute maximum mass was only about 0.7 times the mass of our sun. I mean, talk about a downgrade. This became known as the Oppenheimer-Volkoff limit, and it turned the whole field upside down. Okay,
So for decades, that was the law of the land in physics. 0.7 solar masses. That's the limit. End of story. Any heavier, and it has to be a black hole. But then we started pointing our telescopes out into the universe, and what we found, well, it didn't quite match the theory.
So, did they nail it? Was the mystery of the cosmic weight limit solved way back in 1939? You can probably guess the answer. The universe, as always, had other plans.
Yeah, not quite. See, as our telescopes and techniques got better and better, we started being able to actually weigh these distant neutron stars. And when the data started coming in, astronomers found a pretty big problem. The numbers just weren't adding up.
And a big problem is an understatement. They started finding neutron stars that were more than 2 times the mass of our Sun. I mean, we've seen them at nearly 2 solar masses, even over 2.1. According to the Oppenheimer-Volkoff limit, these things are impossible. They shouldn't be there, but they are.
And this chart just lays out the whole drama perfectly. You've got Landau's original calculation way up here at 6 solar masses, then you have the Oppenheimer-Volkoff limit way down at 0.7. And then you have what we actually see in the sky, these real neutron stars, hanging out around 2 solar masses. So what gives? What did they miss?
Well, the thing is, it's not that Oppenheimer and Volkoff were wrong. Their math was brilliant, but their model, it was a first draft. A monumental first step, for sure, but it was based on a simplified picture of what's actually going on inside one of these stars. Their 1939 model made a few key assumptions that we now know are a bit too simple. For one, they basically treated the neutrons like they were little billiard balls that didn't interact with each other. They also couldn't fully account for the strong nuclear force, which provides its own pushback against gravity. Plus, they assumed the star was just sitting still, when in reality, these things spin hundreds of times a second. And maybe the biggest one, they called it a perfect fluid, but the core might actually be a solid. All of these things add extra support against gravity.
And this quote from a more modern analysis really nails it. That equation of state they used, it's just the rule book for how matter behaves under pressure, and it was the best they had. But deep in the core of a neutron star, the density is even higher than inside an atomic nucleus. We are literally off the charts, in a realm of physics we still don't fully understand.
So in the end, this isn't a story about a failed theory. It's actually a perfect story about how science really works. The Oppenheimer-Volkoff limit wasn't the final answer, but it was this incredibly important step that pointed us in the right direction. It gave us a new, deeper puzzle that scientists are still trying to piece together right now.
And that's where we'll leave it, with this fascinating question. Because that gap, the difference between the 0.7 limit from the theory and the 2.0 plus reality we see in space, that's not a failure. That's an opportunity. It's a huge signpost pointing towards new physics, telling us that deep inside the universe's most extreme objects, there are forces at play and states of matter that we haven't even dreamed of yet.